Thanks for the introduction, and good afternoon, everybody. So the ESRF has recently upgraded all the BPM electronics in their booster ring, and what I'm going to present today is the installation and the results which were achieved with the new electronics which are based on a Libera Spark system. So I will briefly introduce what are the most significant parameters of the ESRF booster ring, and then I will go through the installation integration of the BPM electronics in the ESRF booster, and then I'll present the results. So, in brief, the ESRF booster ring collects the electrons which are accelerated by the range vector to 200 MeV and boosts them up to 6 GeV in 50 milliseconds. That means 50,000 turns, considering the 1 microsecond orbit time of the electrons. And the current has a nominal value of 2.5 milliamps, but can go down to tens of microamps according to the operation mode of the booster. And later on, the electrons are extracted in one single turn of the storage ring, which runs with a current of 200 milliamps. The booster ring has currently 75 BPM blocks, and the electronics which were installed were 25 years old. That called for an upgrade of these electronics. And what's interesting is to know what are the parameters which are interesting for these electronics to fit in a booster ring. And what Scheib, or also ESRF, was looking for is a solution which offers a good price performance. So you don't need probably the best performance and you want to pay the highest price for this electronics. But at the same time, they wanted to have a position and some signals delivered every turn. So that means every microsecond. And a system which is easy to use and doesn't require much maintenance. And IPAC developed Libera Spark for this purpose, which fulfills all these requirements and provides a base not only for booster electronics, but also for other kind of BPM electronics systems for different machines. So going briefly through the system, we have 4 input channels which are coming from the BPM. We have an RF front end which provides filtering and also adapts the signal level to the optimal level for the ADCs, which are 14-bit ADCs at 125 MHz. Later on, there's a system on chip which comes from the Xilinx Link family, which provides FPGA and CPU inside of the same device. FPGA for the fast signal processing and CPU for delivering these signals to the control system and the user. And all the signals which are delivered by this instrument are acquired from an external trigger, which is actually which comes from the external part. So we have an electrical signal which triggers all the buffers. The instrument is reached by the external to a gigabit Ethernet interface, which also provides the power to the system. And since the power consumption was 9 watts only, we were able to implement power over Ethernet system in order to power on the units only with the Ethernet cable. So, concerning the installation, the units are installed directly in the booster panel. So we have these supports which are installed below the bending magnets. And this was an ESRF decision because of the radiation density tests which were run 6 months ahead of the installation, which showed very low radiation dose. And so the electronics are placed just 3 meters far from the BPM blocks. That means that there are 2 advantages of this solution. The first one is the fact that there is no much attenuation introduced by the RF cables, so the signal levels are preserved. The second advantage is the installation cost, which is much, much lower than having long cables. That means 60 meters of RF cables. So the units are there, receive the RF inputs from the BPM block, and are powered over Ethernet, only with the Ethernet cable. Concerning the integration in the control system, which is Tango at ESRF, every unit has its own instance of the Tango device server running on a separate machine, and they communicate with the instrument by a TP interface. On top of that, we have a grouping server which collects all the attributes of each individual instance and provides global attributes to the end user. So the interfacing with the system is much easier this way, so the user has not to go through all the individual stations, but just asks for the data to the grouping server. So let's now move to the interesting part of the talk, which are the results. And the first problem we faced with this, let's say, amount of systems was the synchronization. So what happens there is that there is only one trigger signal which goes around the machine, triggering each unit one by one. And this introduces a delay between the first and the last unit which are triggered. That means 2 microsecond delay, which is 2 turns, and this is not acceptable for having all the systems synchronized. So what at the end we want is to have the acquisition in the ADC buffer triggered at the same time. So we want to have the buffers coherent to each other. So the instrument provides a parameter, which is the trigger delay, which enables to trigger the buffer with a different delay with reference to the external trigger signal. So this is the result shown by this picture, where we have a single bunch peak. You can see the first turn, the second turn, and the third turn. After all the systems are synchronized, we move to analyze the other signals. For example, the turn-by-turn signals, which means position and sum every turn, every microsecond. And the first measurement which was performed, it's obvious, is the monitoring of the beam position for all the systems along the wall extraction cycle that goes from the injection till the extraction after 50 milliseconds. And this picture shows the vertical position. Another interesting measurement which can be done based on this data is the evaluation of the tuning. Basically, if we take only one trajectory from one system and we split this data in different slices, we can analyze the frequency content of these slices, for example, every 500 turns, and plot how the peak of this FFP evolves along the time. So we have first estimation of the beta turn vertical tune along the acceleration, so from the injection till the extraction. And this is a useful tool which will be also inserted in the control. A third measurement shows what's the position or an estimation, rough estimation of the position resolution depending on the beam current. So we were running the booster in a long pass operating mode, that means 80% roughly of field pattern, and we were decreasing the current in steps from 2.5 milliamps, which is the nominal current, to several microamps. And to monitor what the current level was with reference to the nominal current, we were using the sum signal from the instrument, which is a very good estimation of the current in relation to some known current. So we went down from 2.5 milliamps down to some tens of microamps. At the same time, we were also monitoring the RMS value on X and Z position in order to estimate what the resolution is. This is a rough estimation that provided quite good results, some tens of micrometers of nominal current going up to some hundreds of micrometers with the lowest currents, which is more than acceptable for the boostering requirement. So what I introduced so far are two kinds of signals, ADC signals and turn-by-turn signals. There is a third family of signals which are delivered by liberal spark, which are decimated signals. Basically, we take the turn-by-turn signal and we average and decimate this signal by a factor of 64. That means that one sample belongs to 64 turns or 64 microseconds. And this was explicitly required by the ESRF for at least two reasons. The first reason concerns performance, because if we decimate an average signal, we are also reducing the bandwidth of the processed signal. And in this way, we can increase the resolution. The price to pay for that is that we don't have the resolution every turn, but every 64 turns. But from these pictures, you can actually see how the traces are much more clear and are less influenced by the noise. The second reason for these decimated signals are the requirement for the the amount of data which needs to be transferred over the network. So if we have to do some measurements which involve all the stations together, and this is the case of orbit measurements, for example, having decimated data reduces significantly the data which needs to be transferred over the network, and we don't put in crisis the control system. And this is just an example of the X orbit and the Z orbit, which means vertical orbit. And two stations here are missing because they were just installed but not linked to the RF cables. So these measurements are all measurements which can be done also when the machine is running, but we had the opportunity also to analyze some particular cases which are not so often analyzed. And for example, these were the extraction and injection processes. And the purpose of these measurements were actually to go to see if everything works as it is expected to work. And this picture here shows what's the structure of the booster ring in correspondence of the extraction point, which is shown by this red arrow. We have 6 cells from QD38 to QF02, and we have a lot of magnets and BPMs there. Let's start with the bumpers, which are used to produce a local horizontal bump here, so the beam is actually steered here and back, and in order to move the beam toward the extraction point. And this is done 1.5 milliseconds before the extraction. Then we have the second magnet, which is right before the extraction point, and exactly at the turn where we want to extract the beam, a fast kicker enters in action here and provides a further kick to the beam, which is pushed over the second magnet blade and the beam is extracted. So how can we check that everything goes as it's supposed to? We have 2 BPMs right in between the electron bump, and we can check that how the position evolves in time, and we have further BPMs downstream the extraction point. So if we take the horizontal data at this point, we have 2 traces, the red one and the green one, which are belonging to the 2 BPMs which are right in between the bump. So we can see that actually 1.5 milliseconds before the extraction movement, a local bump is created and the beam moves along the x-axis towards the extraction, towards the second magnet blade. And the blue curve shows the signal from a BPM which is downstream the extraction point. This shows that the beam trajectory is not influenced by this local bump, which is created before the extraction. And if you zoom at the last turn, we have actually, we can also see the effect of the fast kicker, which kicks out the beam from the accelerator. And after that, we don't have any more beam for that. Of course, these 6 cases are just a part of the measurements which were done, and more cases can be found in the paper or also in the next presentations. So, to conclude, 75 BPMs were installed in the ring, and the installation, integration, and the first measurements were done in 2 weeks only. And the machine was running, that means that we didn't have the booster only for us, otherwise it would be much shorter. And the system provides ADC, turn by turn, and decimeter data, which proven to be useful for different kinds of measurement. And as a solution, LibreSpark is a cost-effective solution and valuable device for this machine and many other machines. Thanks for your attention.